Hello. Today I will be going to present our paper titled An Efficient Lossless Compression Method for Periodic Signals Based on Adaptive Dictionary Predictive Coding. So this work is based on 2020 Applied Sciences research paper with the same title. So our team members are me, myself, Kaustubh Duse, Rudra Patel, and Yashire. So this project is completed as part of the EC 433 uh, Information Technology course. So let me begin by explaining the problem we are trying to solve. So periodic signals are such as ECG, biomedical waveforms, and power quality signals produce massive amounts of data because they are sampled continuously. This leads to a data explosion problem. So these signals contain repetitive, predictable patterns which introduce high redundancy. So this increases both storage requirements and transmission cost. So let's quickly look at the limitations of existing compression approaches. So one of them is DPCM, which struggles with complex or multi-pattern periodic waveforms, DCT and LWT, which provide a reasonable compression but are often computationally heavy and generally loosey because they require quantization. There are also advanced models like ARIMA or RNNs, which are accurate but too computationally expensive for real-time low-power systems. So overall, there is a strong need for a method that is lossless, adaptive, which has low complexity and designed specifically for periodic signals. So this is why exactly what adaptive dictionary predictive coding provides, which is our project. Now I will hand over to Rudra who will walk you through the proposed ADPC approach and our overall implementation. Thank you.
Proposed method, which is adaptive dictionary predictive coding, ADPC. ADPC predicts the next value of the signal using the previous two samples, and it does the through a two-dimensional adaptive dictionary. If the dictionary already has an entry for the previous two samples, the prediction is uh, s prime of k equals d of s of k minus 2, comma s of k minus 1. If there is no dictionary entry for the pair, then the algorithm uses a fallback linear prediction. That is, s prime of k equals s of s prime of k equals minus of 1 time of s of k minus 2 plus 2 minus of s of k minus 1. After predicting, we compute the error. E of k equals s of k minus s prime of k. This error becomes the compressed output. The dictionary is updated at every step with the new mapping, which makes the method adaptive and capable of learning repetitive patterns very quickly. The main algorithm steps are the first is the check the dictionary, second predict using dictionary or fallback. Third is compute the error. Fourth is update the dictionary, and the fifth transmit the first two samples directly. Uh, uh, then I will talk about our contribution in this. Our contribution includes implementing the complete ADPC encoder and decoder in the Python, achieving perfect lossless reconstruction, ensuring linear of n complexity, and demonstrating strong energy concentration and the error signal, which later helps LZW achieve high compression. Now we'll move to the slide number 4, which is results. Uh, these slides represent the results for our implementation. The first figure shows the error histogram, and we can clearly see that most of the error values are clustered around zero. And this confirms the energy concentration property of ADPC, and that directly improves compressibility. The comparison table, uh, on the other hand, shows the overall performance. ADPC gives the highest compression ratio of 64.9, and DCT gives 46.8. LWT gives 20.7, and DPCM gives 21. So, ADPC outperforms both predictive and transform-based methods while still providing perfect lossless reconstruction and low computational cost. Next, I will summarize the conclusion, and then I will also talk about the future directions. So, to conclude, ADPC offers perfect lossless compression for the periodic signals and adapts efficiently to changes in amplitude and pattern. With its linear off and complexity, it's highly suitable for real-time and embedded application. Our main contribution were implementing the complete ADPC encoder and decoder, reproducing and verifying the base paper's result, analyzing prediction behavior, error characteristics, and performance. I will now talk about future directions that are included. So we adding denoising to improve performance on noisy on periodic signals, extending ADPC to non-stationary or variable period data, and optimizing the algorithm for IoT and low power devices. Thank you.